What you can see in this image in front of you right now is the North Somerset coastline. It's Hinkley Point. And in the image, we have a total of 3.5 nuclear reactors. Down here in the foreground, we have Hinkley Point A and Hinkley Point B. They are two commercial nuclear reactors that have put energy onto the national grid in the UK for many years. Along with, you may see these cranes down here, the construction of a new power plant called Hinkley Point C, the newest nuclear reactor that will be built in the UK. Now, along with these Earth-based nuclear reactors, over there in the background, you can see the sun, okay? And that's the biggest nuclear reactor in our solar system. And it turns out that what underpins the operation of both the nuclear reactors here on Earth and up there in the cosmos is something called nuclear data. It's something you may not have heard of before, but hopefully throughout this talk, you will have a nice introduction to that. Now, what are nuclear data and why should you care? Well, in order to answer the first part of that question, you really need to understand what nuclear really means. Now, everything around us in the world is made from atoms. So my head, your computer screen, everything that you see is made from atoms. And atoms are very, very small, okay? They're less than 1/1000th of a millimeter, so they're incredibly tiny. And at the heart of every single atom lies something called the atomic nucleus. Now, the schematic diagram on the screen here is not entirely accurate because it turns out that that nucleus at the very center is incredibly small compared with the whole atom. Okay, it's around 100,000th of the size of the whole atom, but nonetheless, it carries almost the entirety of the atom's mass. These electrons that whiz around the outside of the atom are very, very light. Now, what we have is we have an object that's incredibly small. It contains a lot of mass, and that means that it's an object that has a high density. Now, to give you some idea of quite how high this density is, I refer to you this image here. Okay, the equivalent density of an atomic nucleus would be to get every single human being on the Earth, all 8 billion of us, and squeeze us into something the size of a playing die. Only then would we have something that is equivalent in density to the atomic nucleus. Now, this very high mass density is very interesting, but what we're really interested in is the energy density, the energy stored within an atomic nucleus. Now, you may well have seen this equation. There aren't many equations in my talk, but this is one you may have seen before. E equals mc squared. It relates the mass of an object with the energy that it stores. Now, if you've got something that has a very high mass density, that means that we have a very high energy density as well. So inside every atom is stored a lot of energy inside the atomic nucleus. How do we access that energy? Well, what we do is we perform nuclear reactions. Now, what you can see on the slides here are two different types of nuclear reaction. The one that's showing at the moment is the kind of reaction that you get inside a nuclear reactor. You have a heavy nucleus, such as uranium. A neutron comes along and splits that uranium into multiple pieces, releasing energy. Now, inside the nuclear reactors in the cosmos, the stars, such as our sun, we have different kinds of reactions. We have something called fusion reactions, where you have two small nuclei meet together, and the fusing of those nuclei together gives a release of energy. Now, looking at these different reactions, the fission, the splitting of the nucleus, the fusion of two nuclei, there are a number of questions that we could ask ourselves. When you bring these particles together, what's the probability of that reaction happening? Okay. If the reaction takes place, what reaction products would you get? What are the final state particles that you have? The particles that you end up with, are they radioactive? Are they safe? And we could also ask in this reaction how much energy is released. Okay, so these are all very important questions, and they all fall under the banner of something called nuclear data, this term that you may not have heard of before. And nuclear data, I'd say, is a database of information about a variety of nuclear reactions that scientists have gained from doing experiments over the last 70 years. Okay, every time somebody does an experiment, it contributes to this database of nuclear data that we can then use to model systems like nuclear reactors on Earth and stars up in the cosmos. Now, why should you care about that? Okay, and hopefully that's the question that I'm going to answer throughout the rest of my talk. Let's begin with nuclear data on Earth and how it's used to understand what's going on in these things, nuclear reactors here. Now, this is a TEDxAberystwyth event, and as far as I know, these are the decommissioned nuclear reactors that are closest to Aberystwyth. They're in the Snowdonia National Park. Now, why is this important? Well, it turns out last year, the UK passed a bill committing us as a country to reduce our greenhouse gas emissions to net zero by the year 2050. Now, that might just seem like a number in your mind, so let me put it into perspective. In real world terms, that means that we have to reduce our carbon and greenhouse gas emissions by over 80% compared with the levels that they were in the year 1990, coincidentally the year that I was born. Now, the good news is we've already reduced our CO2 emissions since 1990 by around 40%. And the way that we've done that is we've closed a lot of the coal-fired power stations. However, okay, we only have 30 years left, and in order to bridge this gap from 40 to a reduction of 80% in real world terms, love them or hate them, it's predicted that nuclear reactors in some form will play a significant role in the UK's energy future. Now, this diagram here shows a nuclear reactor, and all of the heat exchanger stuff on the right-hand side there, we're not going to talk about that. All of the interesting stuff is happening in something called the reactor core, which is this orange and gray area on the left of the image here. This is where all the interesting nuclear physics happens. So let's zoom in and have a look at some of the nuclear fuel that we're dealing with here. So if we zoom in, what you'll see are atoms of uranium, and at the center of every uranium atom is the uranium nucleus, which is what you see here. Now, in a nuclear reactor, just like this, neutrons come along, slow-moving neutrons. They split the uranium atom into multiple pieces through a process called nuclear fission, and that splits the nucleus into several fragments along with some other neutrons. Now, what happens next is crucially important, as you're about to see. Those neutrons can then go on and cause further fission reactions, which will then produce more neutrons, and what you get is something of a chain reaction. What that means is to carefully control the number of neutrons that are propagating through your reactor at any one time is absolutely crucial for the safe and efficient operation of those reactors. Now let's have a look at some of the interactions that those neutrons may undertake while they're in the reactor. So some of the neutrons will scatter. So just as we're going to show here, they will scatter. That will slow them down to a point, to an energy where they can then induce another reaction, releasing more energy. Now the problem is that with some reactor materials, the probability of those neutrons scattering through a particular angle at a particular energy is only known with around 35% accuracy. Okay? Now, this is something that we wish to reduce. Some neutrons can also be absorbed. So what you can see here, a neutron may be absorbed by another nucleus that's contained in the reactor before it meets another uranium, meaning that no more energy will be released due to that neutron. However, the problem is that the probability of those neutrons being absorbed at some of the energies is only known with around 30% accuracy. Again, another gap in the nuclear data that we would like to resolve. Now, finally, and this is very important when it comes to radioactive waste, is that some of the neutrons will slow down in the reactor. They will induce another fission reaction, and the nuclei that you're left over with may themselves be radioactive. That means that they will throw gamma rays or beta particles or alpha particles into the surroundings, which is obviously important for nuclear waste storage, but also the energy released by these gamma rays into the reactor itself is only known to around 10% accuracy. And again, this is something that we'd love to improve through measurements and improving the nuclear data that we have. So nuclear data is clearly very important, okay, in terms of nuclear reactors here on the Earth. To control the nuclear reactor, we need to know the number of neutrons that are scattered and absorbed within the reactor. If a neutron meets some uranium, what is the probability of it splitting? In terms of nuclear waste and the heat that's produced by the reactor, we need to know what radioactive nuclei are produced and in what amounts, and also how they decay. Do they decay by alpha, beta, or gamma emission? And then finally, in terms of the fuel inventory and the efficient operation. Now, it turns out that refueling a nuclear reactor is a little bit trickier than refueling your car. Okay, you have to get a crane, lift the top of the reactor off, and remove radioactive material. So if we can simulate through computation, okay, these reactions that are happening inside the reactor and learn how much fuel is used and in what parts of the reactor, that's a real advantage in reactor operation. Now, it turns out that the nuclear data that we currently have on file is sufficiently good enough to safely operate the nuclear reactors that we have currently in the UK. But as I mentioned at the start, we have new nuclear reactors that are currently being built and will be built over the next 20 years. And so really understanding the reactions is going to be crucial to simulate and efficiently build those new reactors. Now, along with being important here on the Earth in order to understand the nuclear reactors here, nuclear data is key to understanding some of the biggest things in the universe, namely stars, such as our sun at the center of our solar system, but also has knock-on effects in understanding the structure of the whole universe. And that's what I hope to get across to you now. Now, people have an idea that our sun, and you might see that it's shining on me right now through my window, our sun is a constant thing that's going to be burning forever, but that's simply not true. Now, at the moment, our sun and other stars like our sun, they use hydrogen as a fuel. Okay, so hydrogen is fused through this complicated chain of nuclear reactions to form helium. Okay, and that's how our sun is currently burning. It's how it's sending out heat and keeping us here on the Earth alive. However, in a few billion years' time, all of the hydrogen fuel in the sun will run out, unfortunately. What will happen is the sun will then begin to fuse other nuclei, such as helium, and turn into a red giant star. Now, in doing that, it will expand and it will actually engulf the Earth. But as I say, it will happen in a very, very long time. Now, these red giant stars are very interesting. They fuse heavier and heavier elements all the way up to iron. And when they reach iron, they shed their outer layers into space. And what that leaves is something called a white dwarf star. Now, a white dwarf star is very small. Okay, it's around the size of the Earth. And gradually that white dwarf star will just dwindle away and disappear into the cosmos. That might seem quite interesting, but it turns out in terms of the evolution of stars, or as we call it, stellar evolution, our sun is a pretty boring test case. Turns out the really interesting stuff happens when we consider the bigger stars in the universe, these giant stars, stars that are 1.5 to 5 times the mass of the sun. When we have stars that are that big, when they finish burning their hydrogen fuel, just like the sun, they will turn into something called a red supergiant. Okay, as you can imagine, that's just a big red giant star. And this is the real key difference. Okay, the red giant star, once it runs out of fuel, once it's reached iron, it won't shed its layers gently into the cosmos. It will undergo an enormous explosion called a supernova. And it's these supernovae that I want to focus on for the rest of the talk. Once the explosion has happened, what you're left over with is either a neutron star or something called a black hole. It turns out that we've actually photographed supernova explosions before. What you see here is an image from the Hubble Space Telescope. And a long, long time ago, there existed a red giant star that ran out of fuel and exploded into the cosmos in an almighty explosion. And what we see here from the Hubble Space Telescope are the remnants of that explosion, all of the outer layers of that star being thrown outwards into space. Now, along with being stunningly beautiful, these supernova explosions are actually really useful for scientists to understand our universe. And the reason for that is as follows. It turns out that these supernova explosions, if we look up into the night sky and we see a supernova explosion in a nearby galaxy or in another nearby galaxy, these explosions actually allow us to measure the distance to those galaxies. I'm going to tell you how in a minute. Now, what that allows us to do is it allows us to calculate the rate at which our universe is expanding. And the universe, as you may know, started off with something called the Big Bang, a huge explosion that threw everything outwards from a singular point. And gradually over time, the universe is getting colder and colder and expanding out to be bigger and bigger. Now, using the data from this expansion, we can calculate the age of the universe, which we get to be around 14 billion years. And importantly here, it's 13.7 billion years, plus or minus, give or take, around 40 million years. And we want to improve that estimate for the age of the universe. Now, how are supernovae explosions used to do this? Well, it turns out that there's a certain type of supernova explosion called a type 1a supernova. And these are really, really useful because they have a fixed known brightness. You might have a supernova explode over here or somewhere else in the sky. They all emit the same amount of light. And that's really important because much like the torch on this phone, if I hold the torch to my phone, very close to the screen here, it's very, very bright. Okay, if I move that torch a lot further back, it will appear very, very dim. Okay, and if I moved somewhere the other side of town, you'd barely be able to see it at all. Now, this is how supernovae are used to measure distances in the universe. If you look at them through a telescope and they appear very bright, you know it's very close to you. If it appears very dim, we can infer how far away it is. Now, the situation isn't quite this clear, and it all comes down to understanding the nuclear reactions that are happening inside stars. Now, these supernovae, their brightnesses they're not fixed. They're kind of fixed, but they're not fixed, hence why I've put it here in inverted commas. The brightness of these explosions actually varies depending on the elements that are contained inside that star before it explodes. Now, if we want to understand the composition of the elements inside a star, that crucially depends on us understanding the nuclear reactions that actually happen inside the star itself. Now, some of those key nuclear reactions, we only know to around an accuracy of 10%. And so in order to more accurately measure the distances to stars, to more accurately measure the expansion of the universe, and therefore the age of the universe, we really need to improve the nuclear data, measure the nuclear reactions that are happening in stars here in the laboratory to better constrain these physical quantities. So the nuclear data is in fact the limiting factor in determining the age of the universe, or at least one of the limiting factors. Now, to conclude, I want to bring you back to this image here, right? So we've seen that the nuclear reactors in the sky, the stars in our universe, are crucial for us to understand the age of the universe and how the universe is expanding. But really, that doesn't affect our life here on Earth very much. What's far more important here on Earth are these things in the foreground, these nuclear reactors, and how they will affect our energy production here in the UK. Nuclear data lies at the core of simulating these reactors, understanding how they work and their safe operation. And what I'd like to advocate is continued research by people like me into nuclear data, into these fundamental nuclear reactions, in order to better forward our nuclear program here in the UK, building a nuclear data infrastructure. Thank you for your attention. I'm Robin Smith at TEDxAberystwyth.